In this video, we shall discuss the expectation and variance for the geometric distribution of the moment generating function. For more on this topic, you need to subscribe to this channel. We should recall that the moment generating function for the geometric distribution is PET all over 1 minus QET. Of course, to obtain the expectation of x with respect to t, the expectation of x is the first derivative of the moment generating function at t is equal to 0. So if we take the first derivative of this at t is equal to 0, we'll get the expected value of x. Now, to get the expected value of x, it then means that our moment generating function, that means the first derivative, will now be equal to v, the u all over the t, minus u, the v all over the t, all over v squared. We shall use what is called the quotient rule of differentiation to differentiate this to get our expected value of x. Of course, this will be our u and this will be our v. All we need to do is to substitute the values for u and v and differentiate where needed from the formula given. It then means that our expected value of x is equal to the first derivative of the moment generating function will be equal to, now will be equal to, here we have v, this is v, we have 1 minus q et. We have the u all over the t. The u all over the t, if we differentiate this, we get the same function. So we have p et. Now, minus, we have u. U is p et. Now, we'll differentiate this. The v all over the t, we'll differentiate this. The v all over the t, we have minus QET. So this is what we'll get. All over V. This is our V, 1 minus QET all squared. So this is what we get. Now, our expected value of x, which is equal to the first derivative, will give us the whole of this. 1 minus QET PET plus this multiplied by this, we have QET PET all over 1 minus QET all squared. We can also open this, which means our expected value of x is equal to the first derivative of our moment generating function, the first derivative of our moment generating function. Now, we multiply this by this to give us PET. We multiply this by this minus QET PET plus QET PET all over 1 minus QET all squared. Of course, we note that this will cancel this, since -1 plus 1 is equal to 0. So this will cancel this, and we'll be left with our expected value of x, which we'll write here. We'll come over to this side. We come over to this side. For more on this topic, you need to subscribe to this channel. So to get our expected value of x, which is equal to the moment generating function, the first derivative of the moment generating function is equal to p et all over 1 minus q et all squared. Now, at t is equal to 0, we have our expected value of x to be equal to p, anywhere we see t, we put 0 all over 1 minus q e 0, which is equal to p all over 1 minus q squared. We can recall that if p plus q from probability theory is equal to 1, it implies that p is equal to 1 minus q. So if p is equal to 1 minus q, we have this as p to be p squared, which is p all over p squared. Of course, we haven't gotten our expected value of x. So we also move over to this other side so that we can get our expected value of x. For more on this topic, you need to subscribe to this channel to get more tutorials on moment generating function. Hence, our expected value of x will now be equal to, of course, this will cancel this. It then means we get 1 all over p. 1 all over p. Also, we are to calculate for the expected value of x squared. The expected value of x squared is equal to the second derivative of the moment generating function at t is equal to 0. So, as t is equal to 0, if we differentiate our function the second time as t is equal to 0, is our expected value of x squared. So we recall that our first moment is p et all over 1 minus q et squared. Of course, we have to differentiate this. As we are differentiating it, it means we are taking the second derivative. As we take the second derivative at t is equal to 0, is our expected value of x squared. We should also note that the expected value of x is 1 all over p, because we'll also recall it when we are looking for our variance. Now, this will become our u again, and this will become our v. We'll also use the quotient rule formula for calculating this. So we use the quotient rule. It then means that our expected value of x squared is equal to our second derivative of the moment generating function, which is v du all over dt minus u dv all over dt all over v squared. All we need to do is just to substitute the values for our differentials of this into the formula. Now, we have our expected value of x. We'll move over to this side to make it easier for us. Now we have our expected value of x squared to be equal to, we have it to equal to our second derivative of the moment generating function, which is equal to, now we have v, this is our v, 1 minus qet, 1 minus qet squared, multiplied by the u all over the t, the u all over the t. If we differentiate that with respect to t, we get pet. Now, minus, we have u. This is our u again. We'll bring it down. Pet. Now, we differentiate this. If we differentiate this function, the v all over the t, we'll get 2 into 1 minus qet 2 minus 1 multiplied by what we have inside, which is minus qet all over 1 minus v squared. This is our v. So we have 1 minus qet. We have square already here. Square. If we square it, we also get what? 4. So it will now be 1 minus qet raised to the power of 4. That is what we get. Now, at t is equal to 0, let's say at t is equal to 0, our expected value of x will now be equal to, anywhere we see t, we put 0. We have 1 minus qe0 squared, pe0 minus pe0 multiplied by 1 minus qe0, 2 minus 1 is 1, into minus qe0 all over 1 minus qe0 raised to the power of 4. So that is what we get. That is what we get. We'll move over to this other side again so that we can now resolve our expected value of x squared. Our expected value of x squared. We should recall that our expected value of x is 1 all over p, because we use that when we are calculating for our variance. All right. So we should note that anything raised to the power of 0 is 1. Anything raised to the power of 0 is 1. So wherever we see 0 there, anything raised to the power of 0, we take it as 1. So our expected value of x squared will now be equal to 1 minus q multiplied by p minus p multiplied by 2 times 1 minus q multiplied by minus q all over 1 minus q raised to the power of 4. So this is what we get. This is what we get. The next thing to do is just to resolve mathematically. Of course, we should also note that from probability that we'll recall that P plus Q is equal to 1. It then means that it then implies that P is equal to 1 minus Q. So wherever we see 1 minus Q, we can put P there. So our expected value of x squared is equal to 1 minus Q is P multiplied by P. 1 minus Q squared, 1 minus Q is P squared multiplied by P minus, this is 2 into P, this multiplied by this, because of this negative sign here turns to positive, and this gives us 2P into P multiplied by Q into PQ, all over, we have here as P raised to the power of 4. So if we open this, we get P raised to the power of 3 plus 2P squared Q all over P raised to the power of 4. This is also equal to, something can come out, we can bring out P squared. P squared can come out here to give us P plus 2Q all over. P can also come out here into P squared. Of course, P can cancel P. It then means that our expected value of x squared, will be equal to P plus 2Q all over P squared. So this becomes our expected value of x squared. This is what we get. Remember, our expected value of x is 1 all over P. We got 1 all over P. Yes, this is how to obtain the expectation for the geometric distribution of the moment generating function. The next thing to do is to look for the variance, is to obtain the variance for the geometric distribution of the moment generating function. For we to obtain the variance, we need to write out the variance formula first, and we'll move over to this side. For more on this topic, you need to subscribe to this channel for more tutorial videos on moment generating function. Of course, we should recall that our variance of x is equal to the expected value of x squared minus the expected value of x all squared. We should recall that our expected value of x is equal to 1 all over P. We also have our expected value of x squared is equal to what we got there, P plus 2Q all over P squared. So to obtain our variance is just to substitute what we have for the expected value of x and the expected value of x squared into the variance. So how do we go about that? We write our variance of x is equal to the expected value of x squared, which is this, is P plus 2Q all over P squared minus our expected value of x is 1 all over p. 1 all over p squared. So we can open this. For we to open this, we'll move over to the other side of the board. For we to open that, we'll move over to this side. Now we have our variance of x to be equal to p plus 2q all over p squared minus 1 all over p squared, which is also equal to the LCM of p squared is p squared. All we need to do is just to bring out this. This will now give us p plus 2q minus 1. So that is what we get. So what do we do next? Of course, this is our variance. What do we do next? We can open this to say p plus 2q can give us q plus q minus 1. Nothing has changed. All over p squared. All over p squared. Now, we know from probability that p plus q is equal to 1. So we have that 1, okay, let me write it out. This is our variance of x. From probability, we recall that p plus q is equal to 1. It then means that our variance of x will now be equal to 1 plus q minus 1 all over p squared. Of course, we have something reasonable there. Of course, 1 will cancel 1 to give us q all over p squared. So this becomes our variance. This becomes our variance, which is q all over p squared. So this is how we can obtain the variance for the geometric distribution of the moment generating function. This is how we can obtain the variance. We've obtained the expectation, we've also obtained the variance. The variance is q all over p squared. When we follow this procedure, it will be very easy for you to compute the variance of the moment generating function. For more on this topic, you need to subscribe to this channel.